Now there is another theorem discussed, Cauchy theorem for finite abelian group, जिसका statement है: if G is finite abelian group, P is a divisor of order of G, P is a prime number, then there exists an element A which is not equal to E belongs to G, such that A to the power P is equal to E, और G has an element of order P. इसका प्रूफ देखते हैं. This theorem is proved by using mathematical induction over order of G. If order of G is equal to 1, then the theorem is obviously true. For now, suppose that the theorem is true for all abelian group whose order is less than order of G. Then we shall prove that if uh, is true if it is true for G. Case first: if G has non-trivial subgroup H is equal to E, then by the theorem, if G has a non-trivial subgroup H equal to E, then G is cyclic and finite and of prime order. If G is of prime order, then certaining G has P minus 1 element of type A is not equal to E. Thus A to the power P is equal to A, order of G is equal to E, and so in this case the theorem is true. Case second: if G has non-trivial subgroup N is not equal to E, if P is a divisor of order of N is a proper subgroup of A, finite abelian group G, and so N is also finite abelian group. Also, order of N is less than order of G by our supposing theorem is true for N. Thus, this means that there exists P is not equal to E in N, such that B to the power P is equal to E, but N is N is a subset of G, and so B is belongs to N is a subset of G. Is B is not equal to E in G, such that B to the power P is equal to E. Now, this theorem is true in this case also, but if P is not divisor of order of N, then therefore G is abelian and N is proper subgroup, and so G by N is also abelian. Now we know that order of G by N is equal to order of G is a divisor of order of N is less than order of G. So order of G by N is less than order of G. Therefore, G is finite and G by N is also finite. So P is not a divisor of order of N. Now P is a divisor of order of G, and so P is a divisor of order of G is a divisor of order of N. So P is a divisor of order of G by N. Thus, by our supposition, the theorem is also true for G by N. Now we will discuss the Cauchy theorem for modern algebra. If G is finite group and P is a divisor of order of G, so P is a prime number, then G has an element of order P. प्रूफ देखते हैं हम इसका. We shall prove that the theorem by using mathematical induction over order of G. If the order of G is equal to 1, the theorem is obviously true. So suppose that the theorem is true for all group whose order of T is less than order of G. Thus we shall prove that the theorem is true for G. Now if W is a proper subgroup of G, if P is a divisor of order of W, since W is a proper subgroup of G, and so order of W is less than order of G. By our supposition, the theorem is true for W is that there exists an element B is not equal to E of W, such that B to the power P is equal to E. Therefore, B belongs to W is a subset of G, and so B belongs to G. Thus, in this case, G has an element P of order P if P is not a divisor of order of W, is that P is not a divisor of order of any proper subgroup of G. If A does not belongs to Z, G, then by theorem A does not belongs to Z if and only if order of NA is not equal to order of G. So NA does not equal to G is that NA is not proper subgroup of G, then P is not a divisor of order of NA. By the class equation of group G, we can write order of G is equal to order of Z plus summation A belongs to Z. Order of G is a divisor of order of NA, where the summation runs over a single element each conjugate class. Since P is a divisor of order of G, but P is not a divisor of order of NA. So P is a divisor of order of G is a divisor of order of NA. So then P is a divisor of summation order of G is a divisor of order of NA. Also P is a divisor of order of G and P is a divisor of summation order of G is a divisor of order of NA. Also P is a divisor of order of G and P is a divisor of order of G minus order of G is a divisor of order of NA. Hence P is a divisor of order of ZA. Thus ZG is not a proper subgroup and then ZA is equal to G. Therefore ZG is abelian, so G is also abelian. By Cauchy theorem for finite abelian group, there exists an element A is not equal to E if such that A to the power P is equal to E or G has an element of order P. Hence proved.